I think I know who it is. I was like, yeah, I know this code, and now like, do I know? Sorry. I'm sorry. Anyway. They know the shit's here. Yeah, no. Smile. Oh, well, there's so many ways that she wants to see you, but it's supposed to be very bad. I ran out of places. Maybe I can have my turn. Oh, that's not your stuff. No. But I can take it. No, not the Wait, you know what? I wanted to pull up
Here's the clipboard for the competent, so math and stat majors, you know who you are. Okay, thank you everybody for coming to the last Tom's Talk of the evening, and I'm happy to introduce these three great students here. Yuta Baba, he hails from Yokohama, Japan, and he's both a stats and history double major. And next year, or actually right after graduation, he's going to be working in California at a company called Snowflake, because he just doesn't have enough of Minnesota. He'll be working as a data analyst. Matthew Carter hails from the exotic city of Minnetonka, Minnesota. He's a math and geology double major, and in the future, Matt intends to go to grad school in either stats or geology, and he wants to use statistical techniques to better understand the environment and the world around us. And Sahidi Rao, she's also from another exotic location, Eden Prairie, Minnesota. And she's majoring in stats also, and someday she hopes to go to graduate school in biostatistics and work in public health. They're going to talk to you about spatial statistics.
Thank you, Laura. Thank you, Laura. So today we're going to be talking about spatial statistics and spatial analysis. And so we're going to look at spatial statistics through the lens of three different data sets that represent three different types of spatial data. And so the three data sets that we're going to be looking at today is Airbnb data in Boston, and this is like the location of Airbnb hosts in Boston. And this is a point pattern data set, and what we want to know about this is how do we describe the spatial distribution of Airbnb hosts in Boston, Massachusetts. And our second data set is mercury levels in the South River floodplain in Virginia, and this is a geospatial data set. And what we care about for this data set is, can we predict where the highest concentrations of mercury are in a floodplain given our observations? Our final data set is an aerial data set, and what this data set is flu hospitalization rates in Colorado by census tract. And what we're interested in is, can flu outbreaks in a region be explained by socioeconomic information of each census tract? So why do we have to use this special spatial analysis techniques? Why can't we just use like maybe a linear regression or something we learned in maybe Math 215 or 245? When we look at a data set that we might have for maybe Math 215 or 245, we see that we have each row we assume is independent. And so this is a general social survey, and we assume that the survey responses for the first person who took the survey is independent of the second person who took the survey or the third person. So if the first person answers that they have never been married, that does not affect what the second person's answer on the survey is. However, when we look at our data set, this is mercury levels in the South River floodplain. We have locations for our data. So we have an X, Y, and Z value where we collected the data, or we didn't, but where the data was collected. And so this can actually have an effect on, we can't assume that the points are independent anymore because points that are sampled from nearby locations, for the mercury example, maybe the mercury can be transported using through water processes or other processes. And so we don't know if the values of mercury concentrations at one location is independent from another. We can actually see this. Here is the mercury concentrations data set again, and one of these plots is indexed by location, and the other is indexed randomly. And so the orders of these points, one is by location and one is random. I'm going to ask for a little bit of audience participation, and which one looks random and which one looks like it might be sorted by location. Yeah?
Is the second one random?
Yes, so the second one's random. And so we can actually, I'll point out a little bit of clustering on the first one. So here is circled areas where the data looks more clustered and areas where the data looks like it could have a relationship to each other. And so we see near the ends, all the data is much lower in the mercury concentrations, and there's this little choke point here where it all comes together. And so this is showing that there is a spatial dependency in our data. And so now we're going to move to Yuta talking about point pattern data.
Thank you, Matt. So I'll be talking about point pattern analysis. So first, let's recap the data. So we have Boston area showing gray, and Airbnb host locations as of October 2018 show blue. We have about 6,000 points in this data set. So let's look at the data closely. Here we have cluster points in the Boston downtown area. So if you zoom in, we have Financial District, Back Bay, and the area around Provincial College. If you see the southwest area, it seems to have fewer Airbnb hosts. It makes sense because it's far away from the downtown area, and also it might not be as convenient. All right, now we see how Boston Airbnb hosts are distributed. Let's what exactly are point pattern data? So point pattern data give you the location of events, and the goal of analysis is to identify the spatial pattern and arrangement of points. So are there any spatial trends in the density of points? Are the points spatially random, clustered, or regular? Also, the mechanism that might have generated this spatial arrangement is of another interest. So with this specific data set, what I'm interested in is whether Airbnb host distribution is dependent on any other information, and whether the points in this data set are spatially correlated. So since our eyes are not good at judging the spatial relationship, we'll be using some statistics to do this. All right, so here we have 4 plots randomly generated. Do you think any plots show spatial randomness? Do you guys have any guess? Everyone? Yep. This one? Yeah. This one. You're correct. Do you guys have any other guess? All right. So it turns out all of them are generated using the mechanism that produces complete spatial randomness. So the point pattern with complete spatial randomness both have empty gaps and cluster points. So what exactly is complete spatial randomness? Complete spatial randomness is defined by two key properties, homogeneity and independence. Homogeneity means intensity doesn't vary over locations. What's intensity? It's the expected number of points per unit area. So to be more simply, homogeneity means that points have no spatial preference. So the chance of a point being on the top right corner is the same as the chance of a point being on the bottom left corner. Another property, independence, means that points are not dependent on other points. So in other words, there are no associations between points. So under these two assumptions, the number of points falling in a region is known to have a Poisson distribution. So sometimes we call the point pattern of the CSR a Poisson point process. CSR is really important for several reasons. And one of the reasons, which is relevant to my later slides, is that CSR will serve as the benchmark against the point pattern that you're investigating to see its spatial arrangement. All right. So here we have another plots which are different from what I previously had. So the one on the bottom, it has complete spatial randomness. And the other plots violate one of the two properties that I just talked about, homogeneity or independence. So the one on the top left is of a cluster point pattern. So as you notice, the points tend to be closer together than CSR. The one on the top right, we have a regular point pattern. And as you might notice, points tend to maintain some certain distance. So those 2 point patterns, clustered and regular, violate independence property because there are some associations between points. On the other hand, the one on the bottom left, we have this one violates homogeneity because points are concentrated on the top right corner, so points prefer some locations over the other. So what can you say about the Airbnb host data? So here's the plot of the intensity of Airbnb hosts. So the highly dense areas are highlighted in yellow, and low dense areas are highlighted dark blue. So as you see, Airbnb hosts are distributed inconsistently with more hosts in the downtown area. So what we have here are inhomogeneous data whose intensity varies location to location. So let's go back to the original question. So what the original question is to identify the spatial arrangement of Airbnb data. So are the points spatially random, clustered, or regular? There are several techniques to do that, and one of them is called Ripley's K-function, or a K-function. So what K-function is defined as the expected number of points within the distance r divided by intensity. So here's the formula for K-function. It looks complicated, but what it essentially does is to calculate the cumulative average number of points within the distance r divided by intensity. So you select one point in the data set, and then you calculate the distance from that point to all of the points. Then you count the number of cases where these 2 points are within distance r, and you do that for every single point. And then you divide that by intensity and size of the area to get the average number of points. And then you divide that further by intensity to get the value of K of r. So here's a diagram that helps unpack this function problem. So here we have many points in the map of Massachusetts. Let's call these points S1 and S2. And we also have distance r of 10, 20, 30 kilometers and so on. So let's investigate the number of points within 20 kilometers of S1 and S2. So there are 3 points within 20 kilometers of S1 and 5 points within 20 kilometers of S2. So we have 3 and 5. So we do the same thing for any all other points in this data set. And then you sum those numbers up and to get the total number of points inside the circle of 20 kilometers. And then you divide the number by intensity and size of the area to get the expected number of points. And then you divide that further by intensity to get 0.067, which is the K value for 20 kilometers. So, so K value is known to is equal to pi r squared under CSR. So we'll be using this information when you compare this with the point pattern of your data to see its spatial arrangement. So let's say you have the cluster data on the left. And on the right side, we have the result for K function. We have the, on the x-axis, we have the distance, and on the y-axis, we have the K value. The black line is what the K function for observed data, the cluster data, and red line is what you expect under CSR. And black line is above the red line. So this is because at each distance, the value of K is bigger for cluster data than CSR. So in other words, this is because cluster data have more close neighbors than what you'd expect under CSR. On the other hand, here we have the regular point pattern. The black line, the K function for regular point pattern is under the red line, what you'd expect under CSR. So this is because regular point pattern have fewer close neighbors than what you expect under CSR. So you can use this K function to identify the spatial arrangement of the point pattern that you're analyzing. But there's one assumption that you have to make to use this K function, which is stationarity. So what is stationarity? So here we have points, and I'm just going to use an example which is like nothing to do with the ABB data. So let's say these show the location of trees, and we're looking at the height of trees. And let's say this tree, the height of this tree comes from a distribution with mean mu1. And height of other trees, these two trees come from distribution with different mean. So let's call them mean 2 and mean 3. Since all the points come from different distribution, you cannot estimate the overall mean of the height of tree. So these means are different. You cannot estimate the overall mean. So in order to estimate the mean, you have to assume that data are stationary, which means that all the heights are coming from the same distribution with the same mean. So if you apply this to K function, so if you apply K function to the data that don't meet stationarity, then the deviation of the K function for observed data from that for CSR might be due to varying intensity rather than the spatial relationship that you're trying to identify. And as we just observed, the Airbnb data we have are inhomogeneous. So you cannot directly apply K function to the data that we have. So what do we do? We use additional information called covariate to estimate the intensity of Airbnb data. So here we have the population density in Boston area. The bright colors show the high population density, and dark colors show low population density. If you so here's a plot with Airbnb hosts overlaid onto the density. So as you might expect, areas with high population density have more Airbnb hosts. And to estimate the intensity, we use a model called point process model to do this. So it turns out there's an exponential relationship between intensity of Airbnb hosts and population density. So we have the log here. And here's the coefficient, the intercept and coefficient for population density. Now we have the estimation for intensity of Airbnb. We can get the K function work. So here's the result. So the black line, which is the K function for the Airbnb data, are lying above the red line, which is what you expect under CSR. So this is suggesting that Airbnb data are clustered after controlling for varying intensity. So now think of the time when you are planning a trip to a city you always wanted to go. and you're looking at where to stay online on the internet. But one thing you want to make sure is the safety of the neighborhood that you're staying at. In other words, is Airbnb host location independent of crime? So let's investigate that in the case of Boston. Here's the data, the residential burglary collected in the most recent 1 year as of when Airbnb data were collected. There are about 1,400 cases. Let's compare this distribution with that of Airbnb hosts. So we see many points in the Boston downtown area, but we also see higher concentration of residential burglary in the area of Roxbury and Dorchester. So how do we identify the relationship between points of two different types? We use something similar to K-function called cross-K function. Cross-K function is defined as the expected number of type J events within distance R of type I event, divided by the intensity for a type J event. So here's the formula for cross-K function. As you might notice, it's really similar to that for a K function. The only difference is that this accommodates the difference in types of events. So we have distance from I to J, and we also have intensity for I and J. For K function, its value is equal to pi r squared under CSR. For cross K function, its value is equal to pi r squared under both types of event being independent. So we use this for to compare the data that you're looking at. So it turns out that crime data is also inhomogeneous, like the Airbnb data. So we use, again, point process model to estimate the intensity using population density. And after, so now that we have two models to identify intensity for Airbnb data and residential burglary. So let's look at that K function, the result. So here, the black line is again is for our data, and red lines is what you expect under both Airbnb and crime being independent. So they're really close to each other, but the black line is under the red line, suggesting that there's some repulsion going on between Airbnb hosts and residential burglary. So what mechanism causes this repulsion, this spatial repulsion, regularity? Unfortunately, this model, the point process model for cross-K function doesn't really tell us the answer for this question. So this is for further investigation. There are several things that we can do for further work, for future work. So as you might notice, the black line and the theoretical red line is really close to each other. So how statistically significant is the result? So due to the way R implements this hypothesis testing, I was unable to answer this question, but this is a feasible task. So that's something I want to work on in the future. Lastly, I only look at the relationship between Airbnb hosts and residential burglary. So can you say a similar relationship between Airbnb and other types of crime? So I'm really excited to explore these topics in the near future. And next, Matt will be talking about geospatial analysis.
Thank you, Yuta. So yeah, I will be talking about geospatial analysis now. And so what is geospatial data and how is it different than point process data? And so what the difference is they're both point data, but geospatial data, point process data is looking at the location of events, while geospatial data is looking at measurements of a continuous attribute over an area. So while Yuta was looking at the locations of Airbnb hosts, my data is looking, we choose the locations that we're measuring at, although we are not measuring. We choose the locations that we're measuring at, but, and so what we're investigating isn't the distribution of our data points, but actually the attribute that they're measuring. And so our data comes from the South River, Virginia floodplain. Here is the river plotted on in red on this map. There is 615 sediment cores that were collected that contain information about mercury data. And so This map is really hard to look at because it has a really bad aspect ratio for a presentation. So instead, we're going to look at this small section for the rest of the presentation, but all of the analysis was done on all of the data. So the goals of geospatial data, the primary goal is prediction, because we have measurements of a continuous attribute at fixed locations, and we want to be able to predict what the values are going to be over the entire area that we're studying. And so we are going to use the mercury concentrations in the cores that are collected, and we are going to try to predict what mercury concentrations will be over the entire floodplain. Before we get into prediction, though, we need to first talk about the difference between first-order trends and second-order trends. So this is maybe a familiar figure to some, but it is it's a plot of atmospheric CO2 as measured at Mauna Loa Observatory. And so we can see that there is a trend of CO2 levels increasing as time goes on, and this is a first-order trend in black as the CO2 levels increase with time. However, there is also a second-order trend, which is a smaller scale variation in red, which is showing seasonal variation in CO2 levels. And we can think about this in our data as there may be overall trends to the mercury concentrations in the floodplain, but there also might be some smaller scale variation that we can study at the same time. And so first, we're actually going to look at some second-order trend analysis. And so the first technique that we're going to look at is called a variogram, and it measures second-order trends. To use the variogram, we need to assume stationarity, as Yuta talked about earlier. And so we are assuming that the mean of mercury concentrations over the floodplain is constant. The mean is the same everywhere, and we are just looking at second-order variation. And so here is a plot of a semi-variogram, and here is the equation for it down here. And this equation looks kind of intimidating, but it's half the average squared difference of points that are h units apart. That still is a little complicated, so I'll break that down a little bit more. And so basically, for the semi-variogram at distance, let's say 500 meters, is going to be, you look at every pair of points that are 500 meters apart, you compare their log mercury concentrations, you take the difference, you square that, and then you take the mean of all those values. And so, if your semi-variogram is lower, it means that your values are closer together. And if the semi-variogram is higher, that means that your values are more different. And so, we can see this on this graph that values that are a lower distance or closer together have a lower semivariance and are thus their values are closer together than points that are further apart. And so what this means is that there is a spatial dependency for points that are closer together, and we end up with values that are more similar. And so we want to use this when we predict our values of mercury in the floodplain. And so we can't use it when it's just in this estimation, so instead we try to model it to get our best fit of our semi-variogram. And so here's our model. It's an exponential model, and so this is fit to our points. And here's the equation for the model. And so I'm going to break down what these variables in this equation mean. So we have the nugget effect, which is the amount that the semivariance starts at in your model. You have the range, which is basically the distance over which points are still spatially correlated. And you have the SIL, which is the regional variance, or the variance of your entire data set. And so we can plug in those values into our equation, and we have our model for our semi-variogram. So now we are going to try to predict what values of mercury will be at different locations based on our observed values. And so the way we do this is we take a weighted average of our observed data points to predict the mercury concentration at point SP. And so how do we figure out what we're weighting it by, what this lambda term is in this equation that we're weighting these observations by? And so It's a little bit of a complicated process, but basically what we're trying to do is we're trying to minimize our mean squared prediction error, which is this term, while keeping all of the lambdas summing up to 1. Because if we don't have all the lambdas summing up to 1, then our predictions are going to be biased. And so basically we're trying to minimize our error in our prediction while keeping it unbiased. And the way we minimize this is using a method that uses Lagrange multipliers, and which we won't get into because of time. And it uses, the important thing is it uses the semi-variogram to calculate variance, which can help us reduce the mean squared prediction error. So I'm going to just go through a little short example that should help explain this concept a little bit. And so let's say we have 4 observed locations, and the thing we're observing is the radius of the points that I made in this block. And so we have this observation at 4 points, and we want to guess what the radius of this point would be in the middle. So we take the distance between our observed points and and the point that we want to predict, and we use that to find our weight or our lambda. And so we find lambda 1, lambda 2, and lambda 3, lambda 4, and then we multiply those by our points, and we get our prediction. So we don't want to just do this at 1 point at a time, or just 1 point. And so instead we do this thing called kriging, where we take this equation that we used and we extrapolate it over a grid. And so we make a grid of our area of interest, or the floodplain in our case, and we basically make this prediction at each point in the grid. And so here is our result of our prediction based in our area. The white is the river. You can see it going through here. And this is our prediction based solely on the points. And this is assuming there are no first order trends. Here are our actual points plotted on this graph, and the color of the point is relative to their mercury concentrations. And this is like log mercury concentrations on the And so we don't want to just assume that there's no first order trends though, because there are certainly other trends that are affecting what mercury concentrations are in the river. And so we are going to try to add in predictor variables. And so there are a couple of things we need for to be able to use a predictor variable. And so the 2 things we need is we need to know that variable at every data point we have, and over the entire grid that we're extrapolating over. Because we can't predict at a point if we don't know what its predictor variables are there. And so the two variables that we have this information for is the floodplain year and the land use data. So floodplain year is the average year between floodings of an area. And so on this map we have our 2-year floodplain is the floods around every 2 years. We have our 5-year floodplain in red, which floods around every 5 years, and our 62-year floodplain in black, which floods around every 62 years. We also have land use data, which includes factors such as whether it's a deciduous forest, residential, industrial, agricultural, and stuff like that. And so now we can make our prediction using these variables. So I'll just put those up, and we can see that the prediction is different for all of these. And like we can plot the points, and we can kind of squint really hard and be like, oh, I think this one looks better than the other. But we really don't know which of these models is the best just by doing them. And so we need to compare our models in some way. So the way we do this is we use a method called cross-validation to predict values at our measured locations using our models. And then we compare our predictions at those locations to our observations, and to try to figure out which model is the best. And so one way that we can compare them is called the mean squared error. And so that equation is right down here, and basically we're just taking the difference between our observed values at those locations and our predicted values at those locations. We're squaring it and we're dividing it by the number of observations. And so basically we want this number to be as close to 0 as possible, because then our predictions are as close to our observations as they can be. And so we see for our no first order trend model, we have a value of about 3.5. For our floodplain model, it's about 2.6. For land use, it's 3.2. And for both, it's 3.5. So this shows that our best predictor variable is floodplain, as it decreases the mean squared error by a more appreciable amount than the land use variable. However, the best model for predicting our data is the one that uses both floodplain and land use. However, now we can plot the residual values we get from that. So this is plotting the difference between our predicted values and our observed values. And we can see that over-prediction in pink and under-prediction in blue. And we see that there is still clustering of over-prediction and under-prediction at these points. Like we can see areas where it's mostly blue and areas where it's mostly pink, areas where it's mostly blue, even in our best models. And so what this means is there are probably predictor variables that we're missing and unable to use based on the data we have. And so what we would like to do in the future with this is we would like to see if there's other possible predictors that we could know over the entire grid and over each of our data points. So a couple of ideas that we have but we couldn't do either due to technical difficulties or the data set that we had are possibly distance from the river, sediment type, or density of vegetation. Yeah. Next will be Sahifi with aerial analysis.
Thanks, Matt. So now I will be talking about aerial data and analysis. The key difference between aerial data and point patterns and geospatial data is that aerial data is aggregated by polygons. So rather than specific points, we now have an area or polygon where each of the total observations in that polygon are calculated. So for example, we might have states, and we can calculate the total population in those states. We can also calculate other factors like median income, percentage of population with a high school diploma, and so on. But today, we will be investigating influenza outbreaks in Colorado. So specifically, we'll be looking at influenza hospitalization rates per 100,000 people from 2012 to 2016, based on data from the Colorado Department of Public Health. And so we want to determine whether these flu rates are spatially correlated, so whether they are dependent on location. So here we have a map of Colorado, just to get an idea of the geography there and why the flu rates might be affected by location. So we have the Rocky Mountains going through the center, and we have cities on either side of the mountain with several more cities on the right-hand side. And here we have Colorado broken down by census tracts. So the flu rate data we will be looking at was aggregated by census tracts, so those will serve as our polygons in this case. And there are over 1,000 tracts in Colorado. So aerial data is common in public health because it preserves the anonymity of the individuals being analyzed. So rather than specific information being tied to an individual, the information is now tied to where that individual resides. So this brings us to our question. Are influenza rates in Colorado spatially correlated? Are they dependent on location? Tracts that are near each other are related in some way because people are constantly moving. We see in this map that there are several cities near each other, so people are moving from city to city, they're commuting to work, students are commuting to school. And because they are moving, they are possibly infecting and spreading the flu to one another. So we want to determine whether this is the case, whether location of a census tract is if flu rates are dependent on that location, and then if they are there socioeconomic factors that can help explain flu outbreaks? Okay, so we define tracts that are close by as neighbors, but how do we quantify the number of neighbors a tract has? One method is Queen's method. It's like a Queen's position in chess, where you can move forward and backwards, sideways and diagonally. So here we have a tract, and all the tracts neighboring it all the tracts surrounding it are considered neighbors. But this is just one method. We can also determine neighbors based on distance. So suppose we have 5 tracts. We can plot points in each tract representing the center. We can then connect the tracts if they are within 75 miles of one another, based on the scale below. So notice that A and E are not connected because they are more than 75 miles apart. We can then link the tracks using an adjacency matrix. So We have the rows and the columns as the tracks, and we'll put a 1 if the two tracks are connected. So for example, A to B, that line has a weight of 1. But there are other ways to weight the tracks. We can also row standardize our matrix, so all the rows sum to 1. So now, for example, A to B still has a weight of 1, but now B to C has a weight of 1/3. There's another method where we can take the inverse of the distance of the neighbors. But for all our analyses today, we'll be using this row standardized weighting method. So now if we look at our data, we can plot the centroids of each tract. You can then connect the tracks that are within 75 miles of one another. And we picked this number 75 because the minimum distance for every tract to be connected to at least one other tract was 75, or was around 70 miles. So to make sure that every tract was connected, and because 75 is a reasonable commuting distance, we stuck to this number. Okay, so and then we can perform that weighting method I mentioned earlier with the row standardization. So we've determined the neighbors, we've weighted them appropriately, but is any of this necessary? Well, we can test for that. We can test for spatial autocorrelation to see if the flu rates are dependent on location of the tract. So recall Pearson's correlation coefficient. So suppose we have variables x and y. We have the correlation coefficient r. It goes between -1 and 1, with 0 being no correlation. So we want a similar statistic that will take into account spatial autocorrelation. So that's what Moran's I does. It's an analog to the Pearson's correlation coefficient, but now we are taking into account the weight matrix, W, and locations I and J, which in this case are two different census tracts. And then X in this case is the flu rate. So Moran's I has some cool properties. It has an expected value of -1 over n minus 1. So n in this case is the number of census tracts, so as the number of tracts increases, I approaches 0. It's positive for cluster values, so tracts that are near each other that have similar flu rates will be positive. It's negative for dissimilar values, so tracts that are near each other that have dissimilar flu rates will have a negative Moran's I. And then it's 0 for no correlation. So the flu rates are not dependent on the tract. So here we have a map of the influenza hospitalization rates across Colorado. And if we calculate Moran's I on our influenza rates, we get a value of 0.058. So this number is small, it's slightly positive, but what does that mean? Well, we can test to see whether it's significant. So we have a null hypothesis where we assume that the flu rates are independent of location of tract. And since we're assuming this independence, we should be able to randomly assign the flu rates to tracts. So we'll do that. We'll assign rates x1, x2, x3, x4, x5. And calculate Moran's I. We'll call that I. And then we'll reassign the rates to tracts and calculate Moran's I again. We'll call that I star. So this is called a permutation. And we can do this many times to get a permutation distribution. So if we do this on our data now, we get this red line, which is the permutation distribution, and this blue line, which is our observed value of 0.058. So with our assumption that flu rates are randomly assigned to tracts, Moran's I 0.058 is an unusual value. It's far from our permutation distribution, so we know that it's unusual, and it's slightly positive, so we know that we see more clustering than expected. Okay, so we've determined that there's spatial autocorrelation with the flu rates, but can these flu rates also be explained by socioeconomic factors? We'll first look at some of the variables we will be modeling. Number of households, we have income, we have race, age, education. And we'll go more into detail on these variables later. But we can start with some exploratory analysis. I'll point your attention to the top row because we want to see how these variables are related to the influenza rates. So we see a slight positive relationship with number of households and influenza rates. A slight negative relationship with income and influenza rates, and a slight negative relationship with percentage of white in the population in influenza rates. So we can model this now. So we'll first ignore that spatial autocorrelation we found earlier and assume that the flu rates are independent. So we'll model using a multivariable linear regression. follows the equation y equals beta plus beta 1 x1 plus beta 2 x2 and so on. So y in this case